says, yeah, one moment. Let me start. So, I suppose first I should make an apology. The point of view of this talk is heavily quantum field theoretic, okay? And I prefer I mean by quantum field theory an algebra of observables and the state thereon, and that's it. Okay? The algebra of observables tell you what is measured in the experiments, and the state tells you the result of the experiments. The combination of the two is what the experimentalist measures. This is the basic framework in which I am going to operate, and I prefer this because for me it is much clearer than writing functional integrals and such things. I am not even sure that the two approaches are equivalent always. I don't understand. I can't connect the two dots in a satisfactory way. Okay, so I prefer this. It is basically non-commutative probability theory, and I will be focusing on that. Okay, the other aspect is that in this talk I will be focusing on the superselection sectors of quantum field theories, in particular of gauge series. Okay? It has been known for a long time that, for example, in QED, there are uncountably infinitely many superselection sectors. Okay? So what do I mean by superselection sectors? It is simply the different irreducible representations of the algebra of observables. That's it. Okay? That's what it means. Okay? So it's like fixing when you fix a superselection sector, you are fixing the analog of the Casimir operators for a compact Lie group. Okay? So this is what is meant by superselection sectors. Okay? And we know that it has been known, for example, already in Haag's book, he mentions this, but it was also known in the context that in QED, in the context he was operating, that although there are superselection sectors, for local measurements, it will not turn up because the particular superselection sectors he was focused on was charge selections, charge superselection sectors. Subsequently, it was found, in particular, I think it goes back to some basic work of Tom Kibble, and later by Froelich, Morkios, Strocki, and later, very recently, by Mund, Reren, and Schroer, that these superselection sectors do have an influence, and in particular, they prove quite explicitly that Lorentz invariance is broken. That is, Lorentz invariance changes the superselection sector. Okay, Lorentz invariance is not a local operator, and it changes the superselection sector. Okay, so this is proved in many different ways, and I personally got interested in this field because I was curious on what happens to how do I say detect these things experimentally. Okay? So the main problem is that these are events happening at infinity. So can there be local measurements? Okay? So this is the curiosity which drove me, at least. And I first, by the way, if I am not clear, just ask me. Okay? I'll tell what I know, and I'll also tell what I don't know. Okay, there are many issues to be settled, and I'll come to those as we keep going. So, any operator which changes the superselection sector is what should be called anomaly. For example, axial anomaly is one example, but that is only one example. There are a huge number of operators which changes the domain. Yeah.
You are stuck on your first slide. Is it by choice?
It is by choice. I'll change it now.
Okay, fine.
It's Sachin, is it? It is Sachin.
Yeah.
Good.
You're stuck. Yeah. If it is by choice, then that's fine.
Yeah. Normalia is instructing people. Okay. So this is the curiosity, and the then I found out, well, actually Sachin is here, so I can talk about it. In the course of our studies, we found out that although the language used was different, there was a very early paper by Abhay Ashtekar and Narayan on asymptotic, what they call asymptotic symmetries at null infinity. And somehow inspired by that, we also discovered in our old paper that in QED, the Gauss law operator interpreted in a slightly different way, which I will explain, shows that there are already the group, the remaining, there is a group of transformations coming from Gauss law, which is not the Gauss law. It doesn't vanish on quantum states, which label the superselection sectors. And we found in our old paper that in QED, you can write them down, and we call them sky group. Sky because of the influence of Abhay and Narayan, and then Abhay and Hansen, where they called it the spy group. So we were somehow led by that thing. And in that paper, we also pointed out that this has consequences in QCD, where one can prove, just like in the QED case, you can prove in QCD that color itself is spontaneously broken because it will change the superselection sectors. I'll come to that in a minute, as we keep going. So this is the history of our journey. And recently, there have been other developments in this field, which again starts from quantum field theory, which originally starting from the Wigner representation theory, where the continuous spin representations, which are called continuous spin, where the stability group of a massless particle E2 is faithfully represented. So the translations of E2 do not vanish on the quantum states. They give rise to infinite spin spectrum. So the algebraic quantum field theory people were very interested in knowing what is the quantum field for this. And it was they were not able to find it, because to write a quantum field which transforms covariantly, you need a certain interchainer between Wigner representation and a covariant representation, and they were not finding it. And eventually, Ingvason proved that it doesn't exist. Then started a series of developments of what they called string localized fields. So these are not the standard quantum fields, but there is a string localized field. So the string localized means the field is not localized at the point x, but it is localized at the point x and a line, and the space-like line from that point to infinity. And causality means in this case that two such fields with two lines, their own tails starting from x and y, if both the points x and y and the tail are space-like, then they commute. That will be the Einstein causality in this case. That's what they proved, and they developed this theory quite a bit. And eventually, I think Schroer and then other people, Mund and our friend Pepe Gracia Bondia in Saragossa and so on, they began to apply it to QED. So in QED also you can find the string localized fields, and they found it, and they claim, they have papers on this where they prove, they claim that the perturbation theory in those with this field is much more convergent than is the case with standard local fields. And it also shows rather explicitly why the Lorentz invariance changes the superselection sector. So this is the set of ideas from which this particular work emerges. And the deep reason why all this is happening is coming from Gauss law. The Gauss law is the equation from which we are starting, and that is the basic ingredient in all these calculations. So let me then go on. Okay. So, what I want to propose now, well, so I want to change. So I want to say, so the hint here is, can we see the super selection sectors? I think that you can, but I mean, it's like saying that I can see gravitational waves until say 20 years ago. Okay, it will be, certain effects are there which in principle should be accessible to experiments, but in fact, if they are accessible, depends on the tools of the experiment. Okay, so can we ever see it? I don't know. Okay, but I will indicate one first hint that there may be physical consequences came from a paper which I put out in the net, okay, where I was trying to understand what is meant by theta vacua for in QCD. Okay. So the problem with, I don't like, as I say, I don't want to mess around with functional integers. So the issue then is, what is this theta state, okay, which people are talking about, and what is the operator which implements the winding number transformation on the theta states with eigenvalue exponential I theta. Okay. I wanted both the state and the operator in operator language. Okay. So the state itself turned out to be quite straightforward to find. It is just a certain Chern-Simons twisted vacuum. Okay. It is not just the Chern-Simons term. I am not doing functional integrals with this Chern-Simons as a vacuum functional where everything diverges. I don't want to do that. I am applying this Chern-Simons twisted vacuum. Yeah. So I'm applying the Chern-Simons term to the vacuum. And I also found what is the winding number transformation. It has quite interesting properties, and it is based on the Skirm model, with which, again, we are very familiar with, having worked on it for a long time. Then I found out that there are what people call large gauge transformations, which are characterized by the Skirm term, Skirm solitons, and which has this correct eigenvalue. But then it was a very great surprise to us that, to me at least, that rotations, the Poincare standard orbital rotations in the Higgs, in the gluon sector, will change this operator. Okay. This is because in the Skirm winding number 1 transformation, there's a coupling of isospin and spin. There's a term tau dot xh, okay, in the winding number 1 transformation in Skirm model, and that term appears here. Okay, as so tau dot xh. So if you just rotate xh, it is going to change. Okay, so you have to change rotate tau also. So you have to correct, to implement rotations, you have to add a certain term to orbital rotations, and when you do that, you can restore rotational invariance. But the rotation has changed its character. It is acquired a spin half from this extra rotation on the Pauli matrices. Okay. Again, this phenomenon is not new. Okay, I should say. I think the first people who found this, well, somehow there is history behind it. It goes back to this Finkelstein and Rubinstein, but then there is a very beautiful papers by Raphael Sorkin and Friedman, who prove that this happens in pure gravity when you have large diffuse. That is, diffeomorphisms, certain kind of diffeomorphisms which are not connected to aridity. Okay, so you are taking 3 manifolds which are not flat, but connected sums of flat manifold with some topologically twisted 3-dimensional spaces, and they proved that in this case, large diffeomorphisms corresponding to what they call rotation parallel to a sphere, I think it is a language, can be quantized to have spin half. Then later, this was found in magnetic monopole theory by 't Hooft and Hasenfratz, and also by Jakob and Rebbe. They found the same phenomenon. And later, in our book with Sachin, Sechkin, and so on the fuzzy sphere model, we found that the same thing happens already in finite dimensions for fuzzy spheres. And it comes from the properties of certain projective modules. So there is so the spin change from orbital to some spinorial angular momentum should be observable. How? I'm not very clear. The reason is that I wanted to take So where would you search for such a thing? The natural thing is to look for the coupling of the axion field eta to E dot B trace. That is a standard coupling in the Peccei-Quinn mechanism, and you try to see how can I measure this term when the angular momentum in the gluon sector is changed. So can I take expectation values and measure this? The problem is that this term does not yield to the expectation values in a simple way. So I wanted to see how is axion phenomenology handled in the literature, and it is not at all clear to me. Because on one side they say there is color confinement, and on the other side they say eta is coupled to E dot B of electromagnetism. I don't understand the compatibility. How with color confinement you can see such a coupling? I don't understand, and I have been asking many people without any answer. Okay? So it may be possible, let me see, to see such thing. So that was a starting point. Now I want to go on to see the content of this particular talk that corresponds to how to discuss QED and QCD in superselection sectors. So I want to understand the QED, these Hamiltonians. So we are dealing in Hamiltonian formulation with operators and states. Okay, so I want to discuss what is meant by large gauge transformations in this language. Okay, the large gauge transformations seem to have been introduced by people doing this asymptotic symmetry. So let me retain that language. Okay, so the approach we take goes back to, again, old work with our group, okay, where Sachin also was involved, and it is reviewed in this review article which I have given here. Okay? And the metric is standard. I think the relativists, GR people prefer -1 at the beginning. So, but I will use this. So the energy is positive. Okay? So, and by gauge group, I will mean the group of maps from space-time to a compactly group. Okay? So that is what I mean by the gauge group. Okay? So it is not capital G, but the group of maps from script G, the spatial manifold to G. Okay? Now, the arguments which are given by this axiomatic field theory people involves some description of infinity automatically. So what is their preoccupation in writing this string localized space? They don't want to work with these indefinite metric spaces at all. Okay? They want to avoid this have indefinite metric space and use BRST or BV mechanisms and go back to Hilbert space. They don't want to do that. They want to work directly on Hilbert space. They're able to do it, but that involves this line I told you from the point X in a space-like direction, and the sector space-like directions happens to be exactly it is basically not the real, it is the de-Sitter space with all possible scales for the de-Sitter space. So it's like a cone. It's like the Rilde space, but rotated. So the space that you get for all space-like directions is this object, and a natural compactification, natural structure so it has a natural section which is a two-sphere. Okay? For a fixed time quantization, the natural section of that space is a two-sphere. So the compactification with S2 is almost canonical in their approach. So I will assume that at infinity, if you want to compactify at all, it should be a two-sphere at infinity. So what does that mean in our actual calculation? So I am not going to, I should say, I am not going to compactify anything. Just a language which is common in physics. Okay? So what I mean by this is that what is the use of this S2? If I take an element G, small g, which belongs to this gauge group script G, then I will assume that G at a point X approaches an element of as X goes to infinity, goes to some point on this S2. Okay, that is what I mean. That is the point at which this two sphere comes in the picture. Okay, but of course, I can also consider a case where this G has no limit at all. Okay? Is that allowed? Whether it is allowed or not depends on the quantum state, and whether when you take expectation values, things start diverging. For example, if the Hamiltonian is not bounded below, in a sector where you consider gauge transformations, where this G does not approach a limit, it could happen. So there are other issues to be faced when this limit does not exist, and I have not considered it. I think it is very interesting to discuss that also, because there is no a priori reason why G should be bounded at infinity. So it may be a convenience, but it should be intrinsic to the problem, and at least I don't know of any intrinsic argument. Okay. So this is just my normalization. I'll work with SUN, and I will use a standard normalization of the generators of the Lie algebra, which is the traces in the n cross n representation and the traces too. Okay? And if I am working with U1, then we can just put the electric charge lambda alpha there. So in gauge theory, so I will not touch the standard Hamiltonian of QCD at all. Okay? So I will not disturb perturbative QCD or anything like that. I will disturb claims of color confinement, which I find very confusing. What they approved, I do not know. Okay? In quantum field theory sense. Okay? But we'll come to that later. Okay? So, but asymptotic freedom, none of these things I will disturb. So, so let me make that point. I won't touch the local physics at all. But I do want to treat the Gauss law in a particular way, which I think we developed over a period of time, again with Sachin's participation, in the following way. Okay? So the Gauss law operator, standard Gauss law in Dirac's language, is covariant divergence of E, okay, the electric field, plus J0. That operator is at each point X is supposed to vanish on the quantum states. But this is not very clear, okay, because these are operator value distributions. So you should smear them with test functions. So the psi of which I have written here is a test function with which I smear this Gauss law, and I'll give conditions on the psi in a minute. And the bracket of the two ends is simply the trace in the internal indices, okay? Lie algebra indices. Okay? Now, this psi, the test function, will also be taken to be a Lie algebra valued test function. Then one can trivially calculate the commutator of this q psi on local fields, and you find that it is a local gauge transformation. Okay? So this will generate the local gauge transformation with this is the potential going to covariant derivative of psi. Okay? So I will allow all test functions, and the Gauss law then will be put this way, okay? With this test function here. Okay? Now the question comes on what boundary conditions I am going to put on this psi. Psi is a class, just a function. Okay? Notice that I am not saying anything about the operators. Okay? Okay. So the okay. Now the point here I want to say is that if we are going to interpret some page skipped, so I want to write this in a different way. Okay? The different way I am writing is something we gathered over a period of time, but it turns out that it is quite common in people in Soberes, in the treatment of elliptic operators on a compact manifold with the boundary. Okay? Then there are so-called Sobolev weak solutions where the operator, say Laplacian, is smeared with test functions with appropriate behavior, appropriate Sobolev space properties in that compact manifold. So you don't write like this. You take this covariant derivative and put it on Xi. Okay? So I write that previous equation in the following way. Okay? So I'm saying that we can partially integrate, and without surface terms, the cascade, the Xi goes to 0 to infinity, and the test function and the quantum state is such that no operator becomes very large at infinity. So with those two conditions, you can rewrite the Q Xi in this fashion. Okay? So the derivative has gone to Xi. So the Gauss law now will be interpreted as Q Xi, where this Xi goes to 0 at infinity. Now, one should be more fine on what I mean by 0 at infinity. Is it L2 at infinity, or is it compactly supported? There are all these fine issues. I would say that I don't completely know how to handle them. What exactly are the bound conditions on Xi to imagine that this Q Xi is a Gauss law on these test functions? I don't quite know. Okay? I do know that in the old papers of Kibble, which Sachin likes very much, and I also liked very much, he takes them to belong to L2 functions on the appropriate spacetime, okay? And appropriate spatial slice. Okay? So that is because the Fock space, the domain of the Hamiltonian defined by the Fock space corresponds to this condition, okay, that the number operator is finite, which can be translated into the statement that the test functions of the, say, free fields are all L2 functions. Okay? So Kibble puts that condition. Maybe that is the right condition. I don't know. So we will simply assume that Xi are appropriate bounded functions at infinity. Okay. Okay. Now, if there are questions, please ask. I hope you can hear me. Can you hear it?
Yes, we can
Hello?
hear you.
Okay, please ask questions. Okay. If on the other hand, once I write like this, there is no reason, a priori reason why Xi cannot become functions, become non-zero functions at infinity. If they become non-zero functions at infinity, there is then absolutely no reason why they should vanish on the quantum states. Okay. So this is the case that Sachin and I considered, where the Xi here becomes has Lie algebra by limits, but they are with the coefficients are functions of the sphere at infinity. Okay? So this is a much larger space, and in fact, it is an infinite dimensional space, and these objects need no longer vanish on the quantum states. Okay? But they do form. Okay. So such Xi which do not vanish at infinity and do not vanish, consequently do not vanish on the quantum states, I generate the Xi group that I and Sachin considered some time ago. Okay? But nevertheless, whatever happens, they will commute with local operators. Okay? Why? Because the locality of the commutation relations on the spatial slice means that it depends only on the local properties of these test functions, and what happens at infinity is not relevant in that case. Okay? So they commute therefore with local algebra. So I should say all local observables due to locality. So what we have got here is that since the observables commute with this local this Qi, these are the fixed points of the action of this Chi group on, say, the naive fields you may write down starting from a Lagrangian. Okay, so doing something with a Lagrangian, you write down the fields, they won't be invariant under the gauge transformations, and you take the algebra and take the fixed points. The fixed points under the script G will be the local observables of the theory. This is a point we have argued many times, starting from a long time ago, and again reviewed in Andres' review, which has been published. So this goes back to old days of people like Pepe Bimonte, Kumar Gupta, and so on. Okay. Now, what I want to do now is, given this Q psi, so this Q psi is a gauge transformation which where the test functions need not vanish at infinity. These are the large gauge transformations, and I will add it to the standard Hamiltonian. So this H0 will be, say, trace of E square plus B square plus the J0 term, and I'll add it, this extra term, to H and call it the chemical potential. Now, we should justify why this is a chemical potential. Maybe the phrase is not happy, but this is the nearest thing I could find. So in any case, this splits into two terms, H0 plus H1, and H1 is this extra term, one coming from large gauge transformations, multiplied by some operator with the scale of energy, so that this equation is balanced in energy. There is time, I'll try to give an interpretation of what this mu is, but notice that this extra term A will not affect equations of motion, because equations of motion are all local. So adding this term, they will simply make gauge transformations. When you commute with H, equations of motion, H0 is not a, H0 will evolve the equations of motion in the standard way, while this one will make gauge transformations on the equations of motion, and that will be local gauge transformations. And since the equations of motion are supposed to be gauge invariant, nothing will happen. So this H generates the same equation using the canonical procedure as H0. It will not affect local equations at all. So that's what I want to emphasize. Okay. I should. So why do I call it chemical potential? Let's go back. Here, if I go back here in Q psi and look at QED, then I can take a particular psi where psi is a constant, say some small lambda. Then this last term is 0, because covariant derivative of this constant in QED is 0, and this one is simply integral of J0 times some constant. So that is the chemical potential in standard language. So this is a number operator added to the Hamiltonian. So the number operator added to the Hamiltonian, which is a U1 global U1 operator, is a chemical potential, and that is here in this, is one of the possibilities for this Q psi. So this is my motivation for calling it the chemical potential, this H1. But if the choice of the phrase is unhappy, we can change it. No problem. I found out after I talked about this, that there are two previous papers where such a term was discussed in the literature in connection with what is called the Savitri vacuum. You may know what is called the Savitri vacuum. One moment. You may know what is called the Savitri vacuum. And these people added this term to see whether the Savitri vacuum is stable under the addition of such a term. And they had some results. So this was pointed out to me by Parthasarathi in Chennai. So I put a reference here. Now there is actually also, I should say, no point in making this mu a function of coordinates, because if it is a function, you can observe the spatial dependence of the psi at infinity is already in this psi in the test function, so you can absorb it there. So there is no point in putting it again. Okay. So the exponentials of this Q psi for different test functions generate this chi group, G, and this group algebra G hat. I call the group algebra as G with a hat. Now, this non-abelian target for non-abelian target group G, this is the important point, such as this U3. This algebra of these Qs is non-commutative. So Q psi1, Q psi2 commutative is I times Q of psi1 with psi2 commutative. So this is algebra that you can calculate using canonical commutation relations, and you find this equation. I can say more on this expression, but let me just look at that. Now, it is important from here immediately to notice that if you take this test functions, say psi2, which are compactly supported, here also the commutator of psi1 with psi2 is also compactly supported. Okay? So if the Qs for compactly supported test functions vanish on the quantum states, is consistent in the entire algebra of these Qs. It is an invariant subalgebra where this Gauss law operators vanish on the quantum states. So the large gauge transformations is an equivalence class of all gauge transformations quotiented by the Gauss law transformations. Okay? It is not a split extension. That is, you cannot find, you cannot split the sky group of Sachin and I into a tensor product of something living at infinity and something in the bulk. It doesn't. That makes no sense. Okay? It will be something like this. Okay? If you take all functions, just give an example. Take a two sphere. Okay? Take all smooth functions from the two sphere. Okay? C infinity functions, and that is a C star algebra. You can take bounded functions. Okay? Now I can ask, are there? Can I find the subalgebra of functions which are localized on the equator? Okay? In this algebra, the answer is no, because to get the subalgebra of functions localized on the equator, you have to consider delta functions. Okay? But delta functions is not an allowed representative in the smooth functions on S2. Okay? But what is done in this context is to quotient the C2, this full algebra, okay, by the subalgebra of functions vanishing on the equator and taking the quotient. Okay. The quotient algebra is what is generally regarded as the representative of the algebra on the equator. Okay. So the quotient is an equivalence class which does not split in that case. What is happening here is a similar thing. Okay. You cannot split it, but nevertheless, you can interpret things as living at infinity in the sense of an equivalence class. Okay. So that is important. Okay. I think I found that it is called, so there is this phrase which I have not fully absorbed. It is called co-invariance. I don't quite understand whether it applies here. Okay. But I found this phrase in some paper by Edwin recently. But what I have been told by, what we have been told, I should say, by M.S. Narasimhan, is that this is related to what is called the causal resolution of certain cohomology. That appears to be the correct description, but again, my understanding of it is vague. Okay. Now, given this algebra, we now know that we can these operators commute with all local observables. Okay? So, in an irreducible representation, I can diagonalize a q psi for psi not vanishing at infinity. That will give me a super selection sector describing the representation of the algebra of observables. No element of the algebra of observables can change it. So, but then here is a problem. This is a non-abelian algebra. So, this vector state I am writing. So, how would I diagonalize operators? Dirac has already taught us that in an irreducible representation of A, we can only diagonalize a complete computing set. So, I cannot diagonalize this. I cannot diagonalize this operator simultaneously because it is non-abelian. Okay? So I will choose some complete computer set. I'll show you examples, and it may or may not be preserved at a time evolution, which is induced by this q psi in the Hamiltonian. So the vector states on the observables are given by diagonalizing suitable operators of q. Okay, but that may not be preserved by the h1 I added to h. Okay, it may or may not. This mu q psi in h is something generic, so it may not commute. It can change it. Okay? So it will. This is a new phenomenon. This means that the chemical potential changes the superselection sector. Okay. This is a new thing that I am finding. I think it is correct. So let me keep going. And of course, I can also choose a mu which commutes with this chemical potential, which commutes with the diagonalized operator. Then it will not change. So there are two cases. One is where this term changes the superselection sector, and one where it does not change. I will interpret the latter for a reason I will give as a color deconfining state. The latter, so the one where this former as a color deconf, I should say, the one where, the form, which is the former here, I should say. If it is, there's something inverted here. So if the vector state is changed by this extra term, I will call it a, for reasons I'll give you in a minute, as a color confined state, and the other one I'll call as a color deconfined state, and I'll give you my reasons for that. And we will see that in case the extra term changes the superselection sector, the orbit or the vector state I have chosen is ergodic in the Lie algebra sense. So it starts from some point of the Lie algebra, and it never goes doubles back to itself. So it is like a real line acting on the two torus. It goes on and on. And one interesting question that comes is, what is the nature of this orbit and what is its closure? I don't know. And there are good physics reasons to discuss this issue, but I don't know the answer. Now, another point. This term I am writing, this mu cas psi in the Hamiltonian is not new. It's already there in, if you do Legendre transformations from a Lagrangian. Okay? This is observed in our old paper, again with this group of people. Okay? Sachin is also there. And it is what we normally write as, it comes from this Fi0 squared term in the Lagrangian. And in the canonical formulation, you get this term. You get covariant derivative A0 EI plus A0 J0. And this A0 has no canonical momentum. Okay? So what is done in practice is to say that this test function, what is done usually is to use the canonical momentum of A0 as a primary constraint, look at its time evolution, and say that after a partial integration, this term vanishes. Because if you can do the partial integration with A0 behaving properly at infinity, then you will find the Gauss law, and the pi0 vanishing, the canonical momentum of A0 vanishing, will give back the Gauss law. Okay? So this is the normal treatment of the Gauss law for this term. But who told us that this A0 vanishes at infinity? And what is the nature of this A0 at infinity? Okay? So that is the issue I am discussing. And what I called psi previously is exactly this A0. Okay? It already is there. Okay? We want to explore its consequences. Okay? So this is a normal treatment, but maybe this normal activity is not correct. Okay. Okay. Now, another point is the following. The extra term in the Hamiltonian will not, of course, because it involves the integration on d cubed x for a spatial slice. Okay? So it will not spoil the commutativity of spatial translation operators with the full Hamiltonian. But with H as the standard P0 with the usual unaltered spatial translation generators, it will look like this. Okay? So with H as the standard P0 and the unaltered spatial translation generators, I write down. So P0 and Pi, I'm adding this extra term. Okay. So I am changing P0 by this extra term, and that involves this test function. So Lorentz transformation will certainly not transform this as a 4 vector. Okay. So Lorentz symmetry cannot be implemented on this Hamiltonian. It will not be part of a Lorentz group. And the scale of this breaking is given by this mu. Okay. This chemical, the energy scale is given by this mu. I'll give an interpretation of this mu later. Okay. So this will mean that Lorentz symmetry is broken at the operator level. But I don't know how much I should worry about this, because there are already many proofs that Lorentz symmetry is in fact spontaneously broken. Okay. So this is compatible with those claims. Okay. And it will definitely not affect local equations of motion. So this activity I'm doing will not show up in classical physics. It will can show up in quantum physics. Yeah. So I again emphasize this point. So maybe drink something to. Yeah. I'm here. Hello. What happened? Can you hear me?
I'm asking a question.
Okay, go on.
So is this Lorentz violation, will it be an infrared effect, or do we know, will it be infrared effect or like a UV effect?
No. These are infrared effects. Okay. As I told you, no, it is coming from one. If you trace back to the old papers, let's say Tom Kibble, what is happening is, well, one can see this way. The charged particle will create an infrared cloud at infinity. Okay? But the nature of the cloud that is coming there, so will depend upon the particular way this electron has come. For example, it may come from a scattering process, or it may come from something else. So the shape of the cloud will change. Okay? So if you make a Lorentz transformation, it will change one cloud to another cloud, and that is. But these clouds are invariant under local operations. You can't change them by local physics at all. And the Lorentz transformation will change this one cloud to another cloud. So that shows already that Lorentz transformations are not local operators. Okay. In the standard quantum physics, they are what are called quasi-local operators. When there is no infrared things, they're called quasi-local operators. But here in QED, it appears that they are not local operators. Okay. And they change the infrared cloud. So they change the shape, all kinds of things. And then they push the system into an inequivalent representation of the local observables. So if you look at the local observables of charges, say number operator, local charge density, or some other operator, F squared trace, F squared in QED, say F mu nu or F mu nu, and so on, they will change their expectation. They will not change their expectation values locally, but their representation will be changed. Yeah. Representation in the Hilbert space will be changed. So there is no unitary operator which will implement them in a given Hilbert space. So this is already clear from this old paper. I should say clear. With some struggle, you can figure it out. Froehlich, Morchio, Strachey explicitly stated in the last paper of Mundreer and Schroer, work out several examples. Okay? So I don't think this is an issue anymore. Okay? This is a fact. Okay? Sorry. Go on.
No.
Somebody wanted to ask.
Because it's clear. Please go on.
Okay. So now So I want to discuss now the dynamics which come from this augmented Hamiltonian. This will be determined by the expectation values of the chosen vector state, where I have diagonalized some complete community sets onto observables. So the vector state will change, could change at time, but the dynamics will be determined by these vector states. But the vector state in particular is also classified by the eigenvalues or the superselection operators, which I diagonalize. It's a complete community set of some sort. So I had to find what is this complete community set. If this complete community set is an abelian subalgebra, it has to be an abelian subalgebra. In QED, this can be simply because QED is abelian already. You can, the conventional choice is Q psi, which is the multiple of the electric charge operator. So you get the charge superselection rule. Different expectation values of this Q psi gives you different charge sectors. But as I said earlier, you can also take psi. You do not go to constant at infinity in QED. Then you get the test functions depending on the spatial coordinate at infinity, under 2-sphere at infinity, and you get what we call as the sky group, and what they represent classically somehow, some roughly seems to be the moments of the electric field at infinity. That's only it's only a classical statement of some sort. But there are these operators. So there are infinitely many operators which you can diagonalize in QED because it is an abelian subalgebra. In they all commute, so you can try to diagonalize as much as possible. I'll make a remark on this in a minute. But in the non-abelian case, this we have to make a choice, and I'll come to the choice now. Okay. So the selected operators become infinite dimensional. So what can you do? I can choose a complete community set from the enveloping algebra with SU3. SU3 Lie algebra. That certainly contains the quadratic and cubic Casimir operators. In the complete community. So they definitely will commute with all the operators. A Casimir, normally, if you are familiar with flavor SU3, a Casimir of an what we call isospin SU2, which is in SU3, a third component I3 of its isospin, and a hypercharge commuting with this I3. Okay, so in addition to these Casimirs, you can also diagonalize commuting sky operators of this kind, and I'll call them. Having chosen this, I can write down this commuting sky operators as Q of psi hill with a tilde on top, but this tilde are linear combinations of this chosen I3 and Y with coefficients becoming functions of x at infinity. So the thing you are getting at infinity is a module of the Lie algebra elements, I should say, Cartan subalgebra elements with coefficients which are depending on the point at infinity. So it's a very large thing. I don't know the representation theory of that object is, I think, not well studied. But anyway, we can proceed with our limited knowledge. Okay. Now, the point I want to make is, having diagonalized the vector state, a generic mu q, this chemical potential, will not commute with this q psi tilde. In generic one. So you might have chosen, for example, the q psi tilde as coming from a particular Cartan subalgebra, and this q cascade I put in q psi I put in the H, which I call H1, may not commute with it. So it will change the superselection sector. Okay. So it will change. It will not change the local observables, and an evolution by the differential equation. It's a hyperbolic equation, but that is not the case with the superselection sector, which is labeling the representation. So it will go on changing. Okay? So this is the new feature of QCD, or any non-abelian case theory. Okay? A generic non-abelian chemical potential will not preserve the supersession sector. Okay? I will discuss this more. I don't. There are implications. I'll mention. I'll give some examples of what might happen, how you may be able to see. But the problem is that can you access it experimentally with the current technology? I don't think. I'll tell you why. Okay? It's like trying to find gravitational waves 30 years ago. Okay? The time scale to observe these things will have to be extremely small. So I'll give some effects which may be accessible to experimentalists. Okay? Which may be at least theoretically accessible. Let's say. So what I will argue is that in case mu q, this extra term changes the supersession sector and its orbit is ergodic, then you can. I have checked. It's very trivial to check that the mean value of colored observables are all zero. Mean value in time. Okay? So if you take, it's like the standard ergodic hypothesis in StatMech. Okay? So if you average, because this supersession sector is changing within the Lie algebra in some ergodic way, you will find that the expectation values also keep changing all over the place. And when you average it, you get zero. Okay? But there is something strange. The Casimir operators, which also are part of the diagonalization process, are not changed by this extra term. They're color singless. So although we will say that the mean value of colored observables are zero, that is not the case with Casimir's. So although the average value of colored observables are zero, nonetheless, I can tell by observing the Casimir's whether it's a 3 star, 8, whatever it is. I can tell, determine the Casimir operators. Okay? So this is not, I think, I'm not very well. I don't know what people doing Wilson lines say about this. What do they say? Can they see the Casimir operators or these charges they are looking at? I don't know. Okay. The second possibility is I choose a term psi which commutes with this psi tilde. So I choose a chemical potential commuting with the diagonalized operators. Then they will not change. Maybe they change by a phase. But if a quantum state changes by a phase, then the vector state, the density matrix does not. Okay? And the supersession sector will not change. Okay? We can think of this. Then there is no problem on measuring mean values of color. Okay? You'll get some number. Okay? And we can call them as characterizing color deconfined phases. So depending upon this chemical potential you choose, in H, you have different phases of QCD which emerges here from. Okay? So let me show some examples. So maybe my phase here is misleading. Okay? What people call as in color confinement, what does it mean? I don't know. Okay? Does it mean that colored states are not in the domain of the Hamiltonian? It must be something like that. But if you say domain of the Hamiltonian, the issue arises, which domain? We have already seen that the Hamiltonian of QCD has uncountably many domains. And which one is chosen depends upon the situation at hand. So what is the meaning of saying that the color, the spectrum of the operator can change from domain to domain? So what is the meaning of saying that colored states are not in the domain of the Hamiltonian? At least it is not clear to me. If I don't know if numerical work based on Wilson lines accomplish results in this context and how it is translated into operator language. So, so I will not, I don't know. Okay? I will not make further remarks on this. Okay? So what I want to make claim is that the formulation that emerges from our work with Parameswaran, Sachin, Sasha, Pinsul, and so forth is a related result, which I mentioned before. The mean values of colored observables averaged over the interaction time are 0 in this phase. Yeah? That is the claim. Yeah? So, mean why? Okay? The reason is very clear. Okay, okay. Let me see. Yeah, the reason is that the interaction time is about 10 to the power of minus 23 seconds in strong interaction. No experiment probes evolution of the system within this time scale. Be it LSC, be it anything else, they are averaging the observables over this period of time. Okay? So, if you have this quantum state which is changing over time, and you try to look at the operator which is average over this time, you get 0. So that is the reason why I claim that this ergodic state I am writing down is actually corresponding, at least as the same physical content, okay, as the standard statement of color confinement. It seems to have the same content as the standard claims. So let me give an example. Okay, where is this ergodic example? So I take lambda 3 and lambda 8, and I simultaneously diagonalize them. So lambda 3 is in the SU3, in the 3. I'm looking at the 3 cross 3 matrix representation. So lambda 3 is the Pauli matrix 3. Okay. Lambda 8 is this matrix 1, 1, minus 2 along the diagonal. They commute, and the joint spectrum is lambda 3 is 1, lambda 8 is 1, this is 1, 1, lambda 3 is 1, minus 1, lambda 8 is 1, second one, and the last one is lambda 3 is 0, and lambda 8 is minus 2. So by diagonalizing them, I'll get a density matrix on the colored observables. Okay? I had to give you a rule for how to diagonalize. At least on paper, I can write down how to do it. Okay? Then I look at the time evolution given by the chemical potential, which is assumed to be time independent. Okay? So the chemical potential in H1, I don't include for now any explicit time dependence. So the picked vector state is an eigenstate of the chemical potential. It will be preserved in time. Okay? So then nothing will change with the colored observables. So let me pick. So if I say pick a why is it not going back? Yeah. Okay. Yeah. So if the picked vector state is an eigenstate of the chemical potential, nothing will change, as I say. Okay. So I want to pick a case where that is not the case, and that is generic. So what do I do is, for example, choose my H1 to be a linear combination of lambda 1, which does not commute to the lambda 3, which I have diagonalized, and let us say, and lambda 8, and this root 3 is for normalization, forget about it. But what is important is that mu1 over mu8 is irrational. So this is very much like the irrational action of real line on a 2 torus. Okay? So I take the quotient, the ratio to be irrational. This operator will evolve the diagonalized state, lambda 3 and lambda 8. But it will not do anything to local observables. So this will be my H1. So, and the two terms in H commute by choice, because H0 is a standard Hamiltonian, which is composed of local densities, which are gauge invariant. So H0 will commute to H1. So I can happily work with H and do computations. But the state 0, 2 is this eigenstate, because in this trivial example I have chosen, this lambda 8 is diagonal in this state, but I don't have to do it, but I just took it like that. So the ergodicity can only show up in the other two states. But this is fine to illustrate the point. Now, the time evolution is given by the q's, I should say, is given by this operator. Rather, q of this xi, which is q of this mu1 lambda 1 and q of this extra term here. And this gives you the action of exponential ith1 on the chosen vector state. But look at the other two states. They evolve in time, and this is irrational. So the coefficient is, so the periods generated by lambda 1 and lambda 8, this second term, are in the other two states, 1, 1 and 1 minus 1, minus 1, 1, they are irrational. So it is like a real line, it never closes. Okay? So the other two states will not come back to the original state at all. In fact, I can prove quite easily that it is even worse. If you choose lambda 3 and lambda 8 from a particular Cartesian algebra and evolve this with this operator, it will jump from Cartesian algebra to Cartesian algebra and in fact never visit back the original one. So this is an orbit, if you like, in the SU3, which is a Lie group. Okay, so it's compact Lie group. So you're getting an orbit which never closes. So it has to be dense somewhere. Where is it dense? I don't know. I discussed with Manolo and other people to find the what is this nature of this orbit, and we had no. I also searched the literature on ergodic actions of Lie groups, compact Lie groups, and I could not find. That's maybe because of my ignorance. I don't know where to look. So this is happening if the ratio is irrational. So, but in the rational case, if it were rational, after a finite number of rotations, in general, it will close back to the original point. And then there is no a priori reason where the averages of, say, color observables cannot need be zero. So those are the two cases I wanted to tell you. Okay. Here is an open question. It is reasonable to ask if the color deconfined faces are attractors for the color confined faces. Is it possible that in some sense, the orbit you get, the color deconfined faces, color confined faces, end up in some limiting sense to confined ones? How do I check this? Maybe one of you have ideas, I don't know. This will involve perturbing them, perturbing the confined face in by some activity, and check whether it goes back to the original deconfined face. But the disturbance I am putting, I suppose, should be unitary. That causes immediate, because I'm dealing with quantum theory, I don't want to lose. This is not a dynamical system. So unitary perturbation of short duration seems inadequate for this task. Why? Once it is switched off by some unitary operator, the system will be in some new vector state and it will evolve by itself. There is no indication why it should go back to the original one. So I also tried to see whether this POVM, this positive operator value measures, would be of help, and I did not make any progress. Maybe the solution somewhere lies in this POVM language, but I did not make progress. So let me see. I suppose that the chemical potential I am dealing with has an interpretation similar to the standard one, where the standard one is the number operator. So in QED, it is a generator of U1 transformations, and it tells you the supersession sector in which it is diagonal. So how do I prepare it? It seems to be connected to the preparation of the experiments. So it appears to be something which prepares the experimental apparatus which is interacting with the system to observe things. So the H1 that is added here seems to be, I want to suggest therefore that this H1 is the term which tells you how the experiment is coupled to the observed system, and observation of appropriate quantum states for this H1 will also give me information on what is happening locally. So let me remind you another thing. But before I go, this is a point made by Sachin. If this cascade has an x hat dependent limit at infinity, xi has an x hat dependent limit. So I can imagine xi approaching different combinations of spherical harmonics at infinity. So I'll get any number of local chemical potentials in QED. So just like the phase diagram of temperature versus this lambda in front of the chemical potential, we will end up getting multidimensional phase plots and multidimensional phase transitions. This is in the abelian case. So this will be already very interesting, whether such a, I have not seen in the literature any such multidimensional plots, but it is already interesting and it seems a feasible possibility. Sorry. Okay. Now, as I say, now there is a problem which I want to draw your attention to. This is, in my opinion, an important paper which was written by our colleagues from Spain and Italy, Manuel Asore, Paolo Facchi, Giuseppe Marmo, Beppe Marmo, Saverio Pascasio. And what they considered in this paper was stimulated by experimental situations. And they were asking, suppose I take the interval -1 to +1 and take the Laplacian as a Hamiltonian, minus the Laplacian as a Hamiltonian. It has a lot of boundary conditions. It is which is characterized by some unitary group. So they asked the question, what will happen if I keep switching the boundary conditions? If you switch the boundary conditions, the domain of this minus del squared changes. So if I try to write the Trotter formula for time evolution, so I write exponential I T1H with the domain D1 corresponding to the boundary conditions, and multiplied by exponential I T2H boundary condition D2. I don't know how to multiply it because these two operators are acting on different domains. So you cannot just add them. The evolution is not one parameter. It is not one parameter subgroup because the operators have different domains. So how do I resolve this? Evidently, Trotter already discussed this issue in his paper. And Paolo, these people found out that the technology involves quadratic forms and domains of quadratic forms, and they gave a formula for this evolution. It is highly non-trivial. Later, there is a paper by Paolo, Giancarlo, these people, Giancarlo and Marilena, which was also published, where they considered a sphere, two-dimensional, say, block sphere, where you have a lot of boundary conditions in the boundary. So in both these conditions, over these cases, they found out how to find the compose the time evolutions. It is not a unitary group, but it involves activities with quadratic forms. And they found in particular, at least in the first case, that there is a fixed point for a long time evolution, and that corresponds to Dirichlet boundary conditions. I have not understood the proof, okay? But that's what Manolo told me. Second case, I don't know the answer. Okay? This is very interesting because such a thing, but that is what is happening in the QCD case that I am considering, where the chemical potential changes the domain, changes the vector state, and hence the domain. If there was such a fixed point, then one can claim that this fixed point is where everything ends up in QCD. Can I find this fixed point? I think this is an open problem. Okay? Yeah. So I think that I will just make final remarks because it's 1.5 hours. Okay. Elsewhere, again, this collaboration, we have argued that quantum observations are done by coupling the experimental operators which form an abelian algebra. You cannot observe non-abelian algebras, period. It's quite trivial. No, of course, we are not doing classical physics. There are no classical frames and so on. Those are figments of imagination to me. If you want to take or talk about the frame, make it quantum. So, given that, if you give me a non-abelian algebra and you ask what is, say, third component of angular momentum, if the algebra is given by SU2, you don't know because there are inner automorphisms of SU2 which can rotate this third component to some other component. So the expectation values can change. So how can I ever measure elements of a non-abelian algebra? This, I think, is the basic problem of measurement theory in quantum mechanics. And Bohr already somehow talked about this by looking at large quantum numbers and claiming that for large quantum numbers, the classical commutative algebra emerges. This point of view has been elaborated in different ways by people like Fiorini and Giorgi Mirzi and Arthur Whiteman, and also much later by Lanzmann. Lanzmann calls these things Bohrification. So in this work on quantum observations, he calls it Bohrification. So what is the situation here? Okay, I want to claim, but let's say tentative claim, so that the idea is the following: this mu, the chemical potential I put, okay, I switch it. So at time 0, okay. So let me see. Yeah. So I suppose that the experiment is initiated at time 0. So the idea is that so at that time we suppose we know the state. I want to know how it evolves from time 0 to some time t, capital T, where under this H0 plus H1. So the initial state is known. Say all the mean values of color observables are 0, and which the experiment knows. Then H1 makes its appearance. I switch it on. So somehow the experiment is tuned to switch on at that time. H1. After time t, I switch off H1. Then I again look at the switch off H1 and again look at the state, expectation value observables. So the quantum state has evolved from 0 to t, and I should be able to tell how it has evolved from 0 to t, and hence tell me what is the dynamics corresponding to H0. So this is a generic idea which is being proposed here, and it appears to be also the same idea that has been proposed by other people. So I have to show, if I want to show this, that there is the data for the evolution from 0 to t is codified in a commutative algebra. So somehow I have to show that the superselection sectors I am dealing with have a commutative algebra underlying them. One moment. I'll just shut the window. Sorry, somebody is moving the lot. Okay. Okay. So I think, yeah. So I think I can prove. I checked this statement with some people doing fundamental algebra, that there does emerge the superselection sectors labeled by a commutative algebra of functions on S2. This appears to be, let's say, tentatively a correct statement. So the states on this commutative algebra will be L2 functions on S2. So this appears to be correct. So if you give me what I will not prove it here, but states on this H1 have a H1 is a algebra. Okay, it is coming from the algebra of superselection operators and characterized by claiming by say C-star algebra of functions on a two-sphere, bounded function two-sphere, with states which are given by L2 functions on the two-sphere. So every smooth function on S2 will give you a superselection sector. That appears to be correct, and it seems that when you look at the quantum state, influences H0, because H0, the superselection sector of H0 and H1 are interlinked. So it's like changing the angular momentum representation by choosing something else, which commutes with it. So, so it's like changing the Casimir operator, for example, for angular momentum. So this is, it seems that is what is happening, but let us say these are issues which I have to think through more carefully. So I think I'll stop here, and if there are questions, please ask. I will try to answer. I think I'll stop here. Thanks. Hello. Hello.
Hello.
I am free. You can ask me a question.
Let us first thank Bal for this excellent talk. And now we will take questions. Any questions? Please go ahead and ask.
Hi, Bal, can you hear me?
Yeah.
Hello. Yeah, so one thing,
Yes.
one of the outstanding problems in non-relativistic QED is the stability of molecules.
Yeah.
And by this, what I mean is that when a molecule is formed, if it is in its ground state, then it, for all practical purposes, there are molecules that are that live so long that you can approximate their lifetime as infinity.
Yeah.
But we know that in QED, these molecules therefore have to be surrounded by photon clouds.
Yes.
And do you think it's possible to think of the stability of molecules as coming from a specific configuration of a photon cloud that corresponds to a particular superselection sector and in the infrared, and therefore the stability of the molecule is related to therefore the molecule cannot really decay into its constituents. I mean, for example, you could say this about chiral. You could, for example, specifically you could say ask this of chiral molecules, no? why is it so hard for chiral molecules to change their chirality? But
Sachin, I don't know. I mean, this is the first time I'm hearing this idea.
yeah. So the thing is that they are surrounded by photon clouds that
Yes.
to a good approximation extend to infinity if it
Yes.
is an isolated
Yes.
molecule. And
Yes.
their molecule is still stable of the lifetime of the order of hundreds of, maybe even thousands of minutes, maybe even years. So it must be that there must be a way to relate molecular physics, the stability
Yes.
of molecules to. I'm wondering if there's a way to relate the stability of molecules to superselection sectors that come to specific superselection sectors that come from the infrared properties of the photon cloud that surround them.
Mm.
So that was one question. I was wondering if it had occurred to you.
I don't know the answer. Since you brought it up, I'll think about it. We can talk.
Yeah.
We'll talk about it.
Yeah. And the other question I had was about this ergodic action that you had. You can't get this particular route to ergodicity. You can't get it for SU2, right?
SU2, no.
Yeah. But
you need
it
at
is
least,
a non-linear, non-Abelian and non-linear theory. So presumably there is ergodicity in the system, but then it cannot be through the mechanism that you talked about today.
No. Yes, you're right. The point is that in the SU2 case, our paper already shows that the diagonalized operators of SU2 is commutative because it is rank 1.
Yeah.
So, while in SU3, well, that's not it. Yeah, the diagonalizable operators, that's not the correct. Wait a minute, let me see. I'm not saying it correctly.
You need a torus.
I may be wrong. Sorry, I understand. I may be wrong. I don't know. So suppose I diagonalize the third component of angular momentum. So suppose I diagonalize the tau 3, okay, in the test function, okay. Then I put a tau 1 term in the that's the point. A tau 1 term in the Hamiltonian H1. Okay? But whatever I put in tau 1, period is periodic. The period may change depending on the coefficient, but it's periodic. The exponential of that is periodic.
Yeah. So that's why this
the
particular
orbit I'm
mechanism
doing
won't
goes
do it.
back to will not work.
Yeah.
This particular mechanism will not work for getting averages of color observable 0.
Yeah.
There may be other mechanisms, but what I suggest will not work.
Yeah.
So, it is the sharp difference is in the rank of the Lie algebra.
Yeah, you need at least 2.
You need at least a torus. It's exactly the same statement as what is an ergodic orbit on a sphere, on a circle, on a true torus. The two torus we know, but what torus we don't know. So yes, it will not work. So one has to understand that. But so I think we should check back with experiments. It's very confusing to me. Let me, since we are here, I'll pose a few questions. First is the following. In perturbative QCD, there are quark jets, right? So when you look at the calculations which are done, each jet carries a particular color. That is how the calculations are done and infrared divergences are handled. But at the end, you get then many jets with color. Then they put fudge factors and combine this color into a singlet. But the fudge factors, so far as I can tell, has nothing to do with QCD. Okay? They are fudges. So is there color confinement in QCD? I don't know. So a similar question arises in the quark gluon plasma, where Sanathan tells me there is a phase transition where color deconfinement occurs. So if there is a color deconfinement, what does it mean? I should be able to see color. If there is color, then I should be able to do scattering. Okay. For example, a finite temperature gas with neutrons, I can see neutron scattering for sure. Okay. So can I see color scattering? I asked both Sachin, Sanathan, and Ajit, and they are not. I don't know what they're saying. Let me say, I could not hear anything which is clear to me. Third point, which is much more interesting, is axion. The axion comes to trace of E dot B, where E and B are not abelian. Okay. The coupling is eta times eta is the axion times trace of E dot B. So how do I detect axion? How do I see this coupling? Both E and B have color. So how do I detect this coupling? I again ask any of you the question. From what I saw, they replace trace of E dot B by QED E dot B. Okay. So there's a coupling to electric and magnetic fields of ordinary QED, and they look at the rotation of the polarization under very strong magnetic fields. But that is not the original coupling. So how did this coupling, last coupling to QED, come from? It is a model due to Sikivi. But where does it come from? I don't know. So these are statements which I would like to understand, but which I failed to. Okay, so yeah, SU2 it will not work. Okay. So yeah, I think there are conceptual issues which have to be clarified. The related question, sorry, there may be more questions. I would be glad to, or have I left everybody cold?
No, go ahead, Bal, with your remark. There are no other questions.
We can close it.
Okay, so let us all thank Bal once again for that excellent talk. And now we will close the session. Thanks everyone for attending.
Okay.
Thank you, Bal.
Okay, bye-bye. Ciao.